Today I'm talking about the backup coverage model. I hope you can hear me because my neighbor, I'm making a lot of noise. The idea is pretty straightforward, right? Let's suppose you have a facility. Let's take a cell tower, for instance. And let's suppose that that facility is running out of service, okay? Then, you still need to cover the demand, and then it's important to have what we call backup coverage. So in case something was to not run properly anymore, or maybe if there was a facility that was running above capacity, then would there be another facility or another set of facilities that could cover the same demand node? Okay? So the definition is pretty straightforward. In the backup coverage, our objective is to locate the fewest number of facilities needed to cover each demand unit I at least one time, so that is the same as the set covering problem, but also to cover demand units I a second time to the greatest extent possible. Now, there can be cases, of course, where the demand units cannot be covered by two facilities. That's fine. But in case it's possible, let's try to maximize this. So we introduce a new variable, a new decision variable that's called U sub I, and U sub I is equal to 1 if the demand unit I is covered by more than one facility and 0 otherwise. To illustrate the problem, I'm going to show you a very simple example where I have demand units which are essentially cell phones, and then where the facilities are cell tower. We're going to show that and then come back to this illustration here on the blackboard. A quick example here to show the mechanism. I have 5 different demand nodes. I'm using all cell phones. Okay. Here I have facilities represent cell towers along with their radius. And now I number the different demand nodes. Now we're checking how we can represent this on the blackboard. Alright, I've tried to illustrate that problem of cell towers and demand nodes here on the blackboard, right? So we have these different cell towers that represent facilities with their respective radiuses. For the simplicity here, I assume the same radius for each facility, okay? So we have 4 of them, and then we have 5 demand nodes. I equal 1 here, I equal 2, I equal 3, I equal 4, I equal 5. Okay, that's the first step. We can see that there are some demand units that are covered more than once, sometimes even 3 times. Okay, and to the bottom left here, you do have this coverage matrix where for each column we have the different facilities, and here each row represents the demand units. And the last column here represents the sum, so how many times a demand unit can be covered by one or more facilities. And we see, for instance, that demand node 1 and 2 can be covered by 2 facilities, while 3 by 3 facilities, and 4 and 5 by a single facility. So now let's look at the formulation of this problem and let's work this out. All right. Let's look at the formulation of the backup coverage. Our objective function is a maximization. We're trying to maximize the number of demand units that can be covered more than once. Okay. Our first constraint here is essentially saying that if a demand unit is covered more than once, okay, then this here becomes 1. Okay. All right. 1 plus 1 equals 2. That means there should be at least 2 facilities here on the left-hand side. Okay, that can cover that demand node. So it's to guarantee it, right? Now, if this is 0, right? So if the demand node can only be covered once, then that's pretty straightforward, right? There would be only 1 facility that can cover it. Second constraint, the number of facilities is limited, maximum of P facilities. We then have the integer constraint, and also we want U sub I to be less or equal to 1. Important to note here, generally U sub I is either going to be 0 or 1. Now let's try to work out this example into the formulation. Alright, after I've shown you the formulation, now we're going to work it out. in a way that is a linear programming file and that Cplex can handle. I hope you can hear me. The neighbors have been making a lot of noise this for Sunday. Alright, so we're going to look at first the objective function. We have 5 demand nodes, right? And the objective is to try to cover this demand node at least twice. So our objective function, I hope you can read it, maximize here, okay, u1 plus u2 plus u3 plus u4 plus u5. Subject to the constraint. Remember the constraint says, okay, if a demand node is covered twice, there must be at least 2 facilities to cover that demand node. So we're going to do demand node by demand node. We're going to look at the first one. So the first one is here, and that one can be covered by both D and C. So we're going to write here xc plus xd should be greater or equal to 1 plus u1. Okay. Second one is demand node 2, which can be covered by both C and A. So we would have then xa plus xc should be greater 1 plus u2. Okay. Third one here can be covered by both C, B, and A. So we would have xa plus xb plus xc greater or equal to 1 plus u3. Fourth demand node here can only be covered by A, so that's pretty straightforward. We have xa greater or equal to 1 plus here u4. Then for demand node 5, that here would be xb greater or equal to 1 plus u5. Subject again to other constraint. The first one is that xa plus xb plus xc plus xd should be less or equal to p. P, we are going to define this later on. Then we have xa, xb, xc, xd should be integer, okay, and then you have u1, u2, u3, u4, and I hope you can see it, u5 here should be less or equal to 1, 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 less or equal to 1. Okay, that sort of forms or worked out our formulation that we can now solve in Cplex. In Cplex, we're going to try to solve this problem. I have written here on the left-hand side of your screen the linear programming as it appeared on the blackboard. We have a maximization function subject to a few constraints. Note here, I have put those bounds right here, ui up to u5 less or equal to 1, the number of facilities that can open. We're going to start at 2 and then we're going to increase gradually up, and the binaries. Okay, I save this here in Cplex. I'm going to read the problem, I'm going to optimize it, and it tells me that if I use 2 facilities, the problem is infeasible. Okay, so go back to when we talked about different type of problems, infeasible, out of bounds, etc. Let's change this to 3 now and see what happens. Change this to 3, optimize it, and I see that there is a solution that has a value of 2. So let's see what the solution is. So display solution of variables. We see in this case that xa, xb, and xc must be open, and then demand nodes 2 and 3 are covered twice. Changing this to 4. Back in Cplex, reading it again, optimize it. We have an objective function of 3, and if we look at the variable, we see that a, b, c, and d are open, and u1, u2, u3 are covered twice. We have solved the problem in Cplex, and now we're going to visualize on the blackboard. Alright, I have now solved this problem in Cplex, and I want to show you the results. Now, we need at least 3 facilities. P should be at least equal to 3 in order to guarantee that every demand node can be covered. If P is equal to 2, some demand nodes will not be covered. Okay, so let's have a look here. So when P is equal to 3, we have XA, XB, and XC that are chosen. So that would be XA would be here. Okay, so that one will be selected. Okay, we have XB selected as well. Okay, and XC is also selected. Excellent. Okay, so in that particular case, okay, we see 3 facilities are selected. Now all the demand nodes can be covered. That's very important. However, and this is relatively important, we only have 2 demand nodes that can be covered at least 2 times, and that would be 2 and 3. No, 1 can only be covered once because we only have C. If P is equal to 4, which is the next step, then we have the same facilities chosen, and in addition we have D that is chosen. And why is this important? Because in that case, now, demand node 1 can be covered twice, and so then the objective function goes up. Okay, so I hope this sort of illustrates well enough the backup covering problem. Thank you for listening.